And we're off to the races. All right. Hello, and thank you for joining us, everybody. If you are watching this video after the session is done, or if you're here right now, I'm appreciative that you are here. Today, we are going to be focusing on all about the final exam for honors chemistry. This session will cover all the content that you need for both my classes and MRS's classes. And the whole focus of this is to go ahead and have you all submit questions so that way we can answer them. I go in the order that they are received. If I've already answered your question previously, your question will be marked as answered, just that way we can keep moving. We all get out of here in a reasonable amount of time. Before we begin, I'd like to talk about the final exam layout, kind of just how it looks. There are 8 overall short answer questions. That's it. There are 5 of them that can be classified as multi-part, but really only one of them is multi-part. The rest of them are like sorting or filling out a table, that sort of stuff. So really, just like one of them is a proper multi-part question. But since some of the questions do have many areas where you need to be putting answers, that's why I've classified some of them as multi-part. Everybody will be getting 60 minutes for the exam, 90 minutes if you have extended time. If you have extended time, you know who you are. In both classes, this is worth 15% of the final grade, 60 possible points. There are 5 points of extra credit possible as well. Additionally, those 5 extra credit points will be given after you turn in your exam. So you need to turn in your exam and then turn in that extra credit after. Now, a question that we're going to get, I'm sure, is can we get the extra credit? How much time do we get for the extra credit? The extra credit time is built into your 60 minutes. So let's say you submit your final exam with 15 minutes to spare. That's great. You get 15 minutes to work on the extra credit. Let's say you submit your final exam, but you only have 2 minutes. Great. You've got 2 minutes to work on the extra credit. If you turn in your exam exactly at 60 minutes, unfortunately, there's no chance for extra credit. We want you to be focusing on the majority of the exam, the more important stuff, versus focusing and stressing out about possible extra credit. There was also a question that I saw pop up very briefly about what formulas do we need to know. Almost every single formula after reaction rates, or including reaction rates, will be given dilutions, pH, POH, all those formulas. The only formulas that are not given are your stoichiometric formulas. Those are if you're going from gram to gram or mole to mole or anything with Avogadro's number. With that in mind, let's go ahead and kick this off. The first question here is concerning about acids and bases. So it says, can we talk about pH and H3O, so the hydronium ion, and the difference between a Bronsted-Lowry and the Arrhenius theory bases, acids and bases? Absolutely. So let's start off with the kind of big thing here, which is pH. Now, pH and conversely, POH, these are measures of concentration. Now, they are both measuring different values of concentration. So this is for pH, this is the concentration of hydrogen ions, H+, or the hydronium ions, H3O+. And for POH, this is your OH- ions. Now, a fun little tidbit that will be given on your formula sheet, but we've got 14 is equal to pH, well, let me rephrase, 14.00 is equal to pH and POH. So if you add them together, they are equal to 14.00. That may be a little different than maybe some of the calculations you've been working on in class, but this is designed so that way all the sig figs work out in the end. For calculating these, all you need to calculate pH you can calculate it from H plus concentration, OH minus concentration, or POH. Now, of course, these formulas will be given on the exam. We're going to do a short example about it before diving into the differences between the Bronsted-Lowry and the Arrhenius theories of acids and bases. For pH, let's say we've got an H plus concentration of, let's say, 1.0 times 10 to the negative 6. And this is molar. So whenever you're dealing with concentration, you need to remember the molar. To go from H plus to pH, you do the negative log, technically it's log base 10, of H plus. So this would be equal to the negative log of 1.0 times 10 to the negative 6, which we all know is 6. So the pH of this concentration would be 6, which would also classify it as an acid. But you may be asking, okay, but what makes an acid and what makes a base a base? That's where we have our two theories. We'll leave this up here for a second if people would like to take a picture and moving in. Let's talk about the Arrhenius theory. I'm just going to abbreviate it A. So the Arrhenius theory for acids and bases, this basically says that an acid an acid will break slash add H plus, no, let's just say add H plus ions to a solution. So good examples of this would be, of course, HCl as it breaks up in water to H plus and Cl minus. A base adds OH minus ions to a solution. So a good example of this would be NaOH, where we have this break up into Na plus and OH minus. Now, the reason why that's important is so that way it's just a nice way we can differentiate this. But we now get into Bronsted-Lowry's acid and base theory. I'll leave this up here for anybody who'd like to take a picture. This will also be made available to each instructor after the recording goes live. We've got the Bronsted-Lowry. Now, the Bronsted-Lowry, this says that an acid donates a hydrogen ion. It also says that a base accepts a hydrogen ion. So, okay, what does this mean? Let's consider this equation. We've got, let's say, HCl plus H2O yields, technically it's in equilibrium, not H2O, let's do NaOH, is in equilibrium with NaCl plus H2O. It's actually a neutralization reaction. Scratch that. Let's start with the original one we were about to do. HCl plus H2O is in equilibrium with Cl minus and H3O. Perfect, better. So here, if we notice that the HCl, as it goes from this side to this side, will lose a hydrogen ion. This makes it, because it's losing a hydrogen ion, an acid. Conversely, we've got this H2O, as it goes from this side to here, it gains a H plus ion, making it a base. And that's really what separates these two theories. Arrhenius's theory says that acids add hydrogen ions to a solution, whereas bases add hydroxide ions to a solution. And let's do this. There we go. And the Bronsted-Lowry says that an acid gains a hydrogen or loses a hydrogen ion, and a base accepts a hydrogen ion. A good way to remember it is acids go away. Acid for A away. Next up, we need to talk about, looks like, reaction rates. Now, that's a big topic, but I'm going to try to break it down into a couple different areas that might be useful to know for everybody to be successful. Reaction rates. So, reaction rates. These are things that influence, or is a reaction rate by definition, is how fast does a reaction go? And that's by definition, right? That's what we're looking at. For the exam, it's important to understand, one, how do reactions occur at the molecular level? And two, what influences reaction rates? So what kind of is going on there? Let's talk about number one. How do reactions occur at the molecular level? It's a great question, right? Now, unfortunately, when we just add two things together, it may look like it happens instantaneously, but in reality, there's a lot of big things happening in that one little mixture. Specifically, molecules need to collide, right? Or in other words, this is called collision theory. So, in order for molecules to collide, right, there's a couple things that need to happen. Molecules need to collide in the proper orientation, right? They need to like kind of go at a proper orientation. If they don't go in the right orientation, they ain't going to react. Molecules also need to go ahead and collide at the proper speed, right, to make that activated complex. An activated complex is the phase where everything's connected before it breaks apart. And finally, molecules need to have the overcome the activation energy. So if you recall these diagrams, like So, right, molecules need to be able to get over this hump there in order for them to react. Now, of course, the second part, how, like, what can influence these sorts of deals? Well, there's a large list that we can go over, but let's discuss like five, right? Temperature can affect it, volume can affect it, pressure, we've got catalysts slash inhibitors, we've got surface area, F, we've got agitation, and several more. But I wanted to make sure that we're keeping moving so that way we don't go on here until 11 p.m. There are several more in your textbooks or on the study guide if you'd like to review them, but these are the big ones that you need to be aware of. I would also recommend reviewing collision theory before coming to the exam. Can you go over reactions in aqueous solutions? Absolutely. We'll leave this here for people to take a screenshot. And we move. Reactions in aqueous solutions. Now, when we mix two things together, not always will they react, right? Some things just don't react with each other. Using this theory of these reactions in aqueous solutions, we can predict what is going to react, and more importantly, what is going to precipitate. A precipitate is a solid, right? It's the solid that is on the product side. So when you have an equation, it's on the right side of those arrows. But you may be asking, okay, but like, how can we predict? If you recall, you were given a little sheet that looks like this, where we've got some stuff on this side, like NO3 minus, we've got O2, SO2, and it says here, if there's any exceptions, what does it react with and what does it not? So you just consult this to see if it precipitates. Note, and this is primarily just for the final, a reaction will not occur if a solid or a precipitate does not form. So a precipitate must occur in order for this reaction to take place. If it doesn't, if no precipitate shows up, how can we tell a reaction's even done? Let's take a look at an example. Let's say we've got, we'll do it easy. We'll do a different color, beige. NaCl, aqueous, plus, let's say, PB AgNO3. And our question is, what are the products? So, right, that's what we're trying to figure out is what forms. Now, when you take a look at this, all this is a double replacement reaction. So you just treat it like that. We've got A, B, C, and D, where we have A goes to D, and we've got C goes to B. This is also aqueous. So we get NaNO3, and according to our rules, that is aqueous. And we get AgCl, which again, according to our rules, is solid. So because it makes a solid, we need to account for that, and that shows that the reaction occurs. Now, we made it a little bit easier for you on the exam, which all this means is that you will not be responsible for the full molecular equations, nor will you be responsible for the net ionic equations. So you don't need to worry about that for the final. It'll be all good. We're going to go through some of these questions. Boom, 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 boom. Can you summarize all the significant figure rules? Sure. Let's zoom this out so that way anybody who'd like to take a picture may. And we're off to the races. Doing good so far, everyone. Let's talk about sig figs. Sig figs do account for some portion of this exam. Note, while there may not be any questions asked directly about sig figs, we will be responsible for maintaining how many sig figs are present throughout your overall equations. Quick coffee break. Let's begin. For addition and subtraction, you round to the least number of decimal places. So let's say we've got 10.00 plus, let's say 15.1. Let's do a 4 here. We would get 25.14. When rounded to sig figs, it would be 25.1. For multiplication and division, you round to the least number of sig figs. So let's say you've got 10.00 times 2. Let's do 10.25, make it easy. If we do this calculation, we would get 20.50. But for sig figs, we can only have one sig fig. So that makes this a little interesting. We can only have one, so this would be rounded to 20 on the dot. No decimal. When you add that decimal, it makes that 0 significant, so we can't have that. If you'd like to go over other significant figure rules, such as what makes a sig fig a sig fig, please submit a follow-up question. But according to your asking about what are the rules are, these are the big 2 main rules that you need to be accounting for. Could you go over specific heat and temperature change? Sure. Wabang. From what it looks like, there are a lot of questions. But we will get through them one by one. If I get to your question and it's already been answered, I will mark it as answered, just so that way we can continue moving forward. The question is about specific heat and temperature change. This is specific to Q is equal to mc delta T. So let's talk about delta T, your change in temperature. This is always final minus initial. So whatever your final temperature is minus your initial temperature, that'll be your answer. It may be negative. That's okay. For C, this is your specific heat. For your specific heat, this is how many joules does it take to raise a substance to raise, I should say, 1 gram of a substance 1 degree Celsius. C will always be positive. Additionally, mass will always be positive, but Q may be positive or negative. Now, can we go over Q metal and Q water? Sure. It relates right to this, so I'm happy that it's right after each other. For calorimetry, so let's say I heat up a piece of metal and submerge it into water. Any heat that's lost by the metal is then gained by the water. A good hint of when you need to use this is if you're given like 2 specific heats, 2 masses, like 3 different temperatures, you'll need to use this formula. This formula is the negative Q metal is equal to the positive Q water. So any heat lost by the metal is then further gained by the metal. Or sorry, let me rephrase. Any heat lost by the metal is gained by the water. So if we have Q and we've got this equation up here, can't we just plug them in? And the answer is yes. Observe. We can say that the negative mass of the metal, I'm just going to do baby M for metal, times the specific heat of the metal times delta T of the metal is equal to, and guess what? It's the same formula, just except this time for water. We've got the mass of the water times the specific heat of the water times delta T of the water. So this is useful when doing these calorimetry equations. Again, you will need to use this formula here, whenever it gives you like 2 masses, 3 temperatures, anything like that. I do want to note one more important thing about this formula, and before we move into our next topic, which is going back to H plus and OH minus, that the final temperature will be the same for the metal and the water. So the final temperature will always be the same for the metal and the water. So that's a very, very good hint there. Another good hint is that your delta T for your metal will be negative. So whenever you have a delta T for your metal, it will be negative, and your delta T for your water will be positive. So those are 3 good hints when solving these equations. So if the formula has both hydrogen ions and hydroxide ions, how can we determine if it's an acid or if it's a base? Good question. Let's head back up here to acids and bases. Now we're kind of out of room. We'll just continue adding on down here. A bing, bang, bong. Let's talk about the pH scale. So if you recall, we are able to calculate pH or pOH given pH, or OH minus, or H plus, depending on what we're given. Once you get them to pH or pOH, now we can determine if it's an acid or if it's a base. Observe. Let's say for your pH scale, if anything is between 0 and 7, it is an acid. So if it's below 7, it is an acid. But if it is above 7, it is a base. Or of course, X is equal to your pH. So if X is between 0 and 7, including 0, not including 7, it is an acid. But on the flip side, if it is between 7 and 14, not including 7, but including 14, it is considered a base. So that makes it nice, easy, and simple. Conversely, we can also determine it if you are given the pOH. So let's say we are given the pOH. You'll notice it's very similar. Again, we've got between, actually, I might just do this. Make my life easy. If it's between 7 and between 0 and 7, including 7, not including, or between 0 and 7, including 0, not including 7, it is a base this time. But if it's between 7 and 14, it is an acid. That is not including 7, but is including 14. It would be considered an acid. So again, as you can notice, it's the very same scale, even down to these markers here, just these guys are flipped. That's the only difference. So if you are given H plus or OH minus, all you need to do is to convert it into H plus or into pH or pOH, and you'll be given the same answer. Talked about acids and bases. We talked about pH and pOH for levels of acids. There's a follow-up question here about, will we have to write out equations with solid and aqueous forms, or will that be already written out for us? You will need to account for states in any and all chemical equations that are on the exam. Do we need to know the orbital box diagrams? No. Will we need to know dimensional analysis or just stoich? For this, you may need to do some metric conversions, depending on the questions that you have. That all that means is going from like milliliters to liters or grams to like milligrams. So you just do the little decimal moving parts. Answer this, Can we go over stoic and the different types of chemical equations? Just waiting for this one. So, three main ones exist. You've got mole to mole. You have mole to gram. I should say there's four that exist. You've got gram to mole. And finally, you've got gram to gram. Let's talk about mole to mole first. For this, I'm going to actually put a key over here so everybody is understanding my shorthand for mole rate. This is your mole ratio. And if I ever say MM, this is your molar mass. So just so that way we're all aware of what my shorthand is, so that way you can account for it in your stuff. An important note here, and for the entirety of the exam, we'll even put it in red. Do not forget units. That includes units in your equations. So you can't forget about those. We need the quantity, unit, and substance that we're talking about with stoic. Observe. And we'll do an example of one of these here in a couple minutes. For mole to mole, this is the easiest of your four possible variations. You have your given amount in moles of your given, and you multiply this by the mole ratio of your given on the bottom and your want on the top. So whatever you're given, right, that's the quantity that you're given, and you're converting it into the quantity that you want. And this gives you your answer in moles of your want. That's your final answer. Bang, bang, bong, right? Easiest of the four. For mole to gram, this one is a little bit more involved than the one above. We'll change colors for this. This is where you are given something in moles and you want to convert it into grams of a different substance. So for this, we have moles of your want. And we multiply this by, you guessed it, your mole ratio of your want on top and your given on the bottom. Note here, or here, I mislabeled this. Moles of your given. Yes. Note here, in both the top one and this one here, we have given here and given here. The reason why they are both here is because we want the moles to cancel out. But we aren't done here, right? That's just mole to mole. We need to add that gram portion to it. So we multiply by 1 mole of your want on bottom times your molar mass of your want on top. And that'll get you your answer in grams of your want. So again, don't forget about here, right? I've got the quantity, I'll use the laser, the quantity, the unit, and the substance. Having all three is important. Okay, but what if we're given grams this time instead? Does that change anything? Unfortunately, yes, it changes the entirety of our little equation that we've got going on. Different color, beige. You've got grams of your given. Now, for stoic, we need the molar mass. This is in grams of your given. over 1 mole of your given. Again, notice here that we've got grams of given here, and we've got the molar mass of grams down here, again, canceling out the grams that are present. We then multiply this by the, you guessed it, mole ratio of your given, again on the bottom, and your want on top. This, of course, will give you your final answer in moles of your want. And that's it. We've got 1, 2, 3. Surprisingly, I find that students have more trouble with these bottom two than with the 3-step. The reason is because these change with depending on what you are given. If you're given moles first and need to go to grams, there's a different path to take versus given grams and going to moles. But then we get to here. I personally find gram to gram conversions the second easiest out of the 4 that we are given. Here, you are given something in grams. Let's say you're given grams, and this is your given. Now, to solve this, we need to do 1 mole of your given on top with your molar mass of your given in grams. Again, canceling them out. Next, we need to do the, you guessed it, mole ratio of your want over your given. Again, we calculate mole ratio from a balanced chemical equation. I really hope it doesn't update while we're doing this. Finally, you do 1 mole on bottom of your want, and then we have your molar mass of your want in grams. Doing these 4-ish steps, we get our answer in grams of your want. To calculate your mole ratio, this again comes from a balanced chemical equation. So we need to have a nice balanced thing before we can even start diving into other stuff. This should be your second step after identifying what are your products. Say, for example, we've got this. N2 plus H2 yields NH3. Again, we balance this like normal. We've got a 3 and a 2 here. So if we're looking for the mole ratio between, let's say, H2 and ammonia, NH3, this would be equal to, for every 3 moles H2, we get 2 moles NH3. And that's it. Solving for H plus and H3 are the same for this exam? Yes. Do we need to know about Kw, where 1.0 times 10 to the negative 14 is equal to the product between H plus and OH minus? It is a useful equation to have on your belt, but you don't need it for this exam, as you can solve those questions in different ways. What equations do we need to memorize? Well, you shouldn't memorize them, you just know them. Anyway, for any equations that you need to memorize, The only equation, looking at the final right now, that is not given. Let me actually just make sure. We'll take a quick coffee break really quickly. There is only one equation that is not given that we've already kind of covered here. Well, I guess like five if you count stoic. Any stoic equations are not given, so you need to be aware of how to get from one thing to another. The other one that is not given is actually here. This one here, where your negative Q metal is equal to your positive Q water. But it's pretty, the reason why we didn't put it is because it's pretty intuitive, where we have the any heat lost by the water or any heat lost by the metal is then gained by the water. And then we're done and dusted. That's the only one. All the other ones will be given as long as you know stoic. What theory should we use to determine if it's an acid or base on a test? It will tell you what theory to use. That's it. So if it says, according to the Arrhenius' theory, organize these in acids, bases, salts, or none, then you know what to need to use. If it says, according to the Bronsted-Lowry definition, talk about acid, base, conjugate acid, and conjugate bases, you'll know what definition to use. It will tell you very clearly and plainly. Will we have to write out the definitions of any of the terms? No. Maybe collision theory. Can we talk about acid, base, salt, or none? Sure. This is mainly for the Arrhenius' theory of acids and bases. For those of you who are raising hands, I am not going to be hitting any of the raised hand stuff. I request that you just put a question in. Makes my life easier. So, perfect. We've got just enough space here. So, for these questions about if something is an acid base, none, or a salt, this is specifically using Arrhenius' theory of acids and bases. Acid, base, salt, or none. For an acid, if on the exam, if it starts with a H plus, with an H, it is an acid. There is one exception. That exception is acetic acid, where acetic acid is H3 or CH3COOH. This is an acid. This is acetic acid. If the formula starts with, or let's say has, OH in it, it is considered a base. Okay, pretty simple, right? An example, of course, would be NaOH. If a formula is ionic, that does not include OH minus or a oxygen ion, and an oxygen ion acting as your anion, right? This makes it a salt. And finally, if it doesn't hit any of those three definitions, it's none of them. A good example of these are hydrocarbons, and that's it. So if it starts with an H, it's an acid, with the one exception of acetic acid. If the formula has OH, it is a base, sodium chloride. If the formula is ionic, with a big caveat there, it cannot have hydroxide or an oxide as an anion, then it is a salt. How many questions are from the first semester and how many versus the second? If according to the study guide, almost everything is from the second semester. The only things that really aren't are nomenclature and a little bit of like metric conversions, if that's a question that you have. Do we need to determine conjugates? Yes. Let's discuss them. This is specifically relating to the Bronsted-Lowry definition of acids and bases. So I'm actually going to go ahead and copy this thing that I made up here. This thing here. So recall this. We've got acids, bases here. But we've got an important thing here. This backwards arrow. Now, all that backwards arrow means is that if we look at it from the reverse direction, this H3O, as it goes into H2O, this loses a hydrogen ion. This makes it an acid, but because it's going in the reverse direction, it makes it a conjugate acid. The reason is because it's going in the reverse direction. Conjugate, all that means is that it's in the reverse. So if we look at this chlorine, we'll use bright pink, and we compare it to our HCl, it is gaining a hydrogen ion, so that makes it a conjugate base. And we're done and dusted. That's all this is. All that fancy word conjugate means is it's going in the reverse direction. A good tip, a fantastic reminder. If something, or let me rephrase, acids become conjugate bases. Always. So if you look here on this one, the HCl was an acid and becomes the conjugate base. Bases become conjugate acids. And that's it. Always. So once you identify the acid and the base, you've actually done the entire question. You've identified the other two ones, which are conjugate acid and conjugate base. Done this one, do this one. We've done different types. Okay. Sorry, just catching up on marking some of the questions completed that we've already done. Looking at the time here, I'm happy that we marked it at around 9:30-ish as our end. Can we go over neutralization reactions? Yes. So when acids and bases combine, they make a salt and water, always. Neutralization reactions are also examples of double replacement reactions. So let's do an example. Let's say we've got H2SO4. What's the name of the acid? Sulfuric acid, correct. This is aqueous. Plus, let's say we're working with, I don't know, lithium hydroxide. Again, aqueous. A question would be, what is the neutralization reaction? Or what is produced by these two things? And guess what? You already know how to do this. It's a double replacement reaction, which that just means that this hydrogen goes with the hydroxide, and this lithium goes with the sulfate. And you just plug them in like that. So we get H2O, and we get Li2SO4. Now, if we're being technical, the H2O is a liquid, and the LiSO4 is aqueous. So, you now need to ask yourself, am I done? Get it carefully. No, we are not done. We need to balance. So after we balance, there'll be a 2 here and a 2 there. Now we are good to go. Do charges matter in this unit? Yes. We actually just saw an example of it right here. Li has a charge of 1 plus, SO4 2 minus, 1, 2, good. Will there be any paragraph short answer questions where we had to make a solution using words from a word bank? There will be a question about there will be a paragraph question on there, but this time instead there will not be a word bank. For endo and exothermic graphs, do we need to know activation energy, temperature, reverse energy, etc.? I would say that is important to know, especially if you are in Miss MRS's classes. Do reaction rate influencers affect solids, liquids versus gases? They do. Almost all of these, especially the ones I've listed here, do affect all of them with the exception of volume and pressure. These are both specifically for gases. Everything else is more specific to all of them. But volume and pressure are more specific to gases. What are the solubility rules? You'll be given a sheet that tells you all the solubility rules you need to know. That sheet looks like this over here, and it will tell you exactly what you need to know. What are the products of combustion reactions and neutralization reactions? Good questions. So these are your products of a neutralization reaction. Let me mark this here, neutralization. For a combustion reaction, these always start off with a hydrocarbon and oxygen gas. For those of you who don't remember what a hydrocarbon is, this is a compound that contains carbon, hydrogen, and sometimes oxygen. Some good examples: C2H6. We've got C6H12O6. O6, sorry, not O2. Again, good examples of hydrocarbons. So for simplicity's sake, we're just going to start off with CH4. Again, that's a hydrocarbon, has carbon and hydrogen in it. This would be a gas. Plus oxygen gas. And this forms always, no matter what the hydrocarbon is, water vapor and carbon dioxide. Always. And then you just need to balance. So we just put a 2 here. We check our counts. Looks like we'll need another 2 here. We're done and dusted. What type of equations will we need to know for a what time of equations will we need to know for aqueous and solutions? What do we need to know? Word, etc. You'll need to know how to write a word equation of a chemical reaction, predict products for these aqueous reactions, and that sort of stuff. Will we be provided a solubility rules with a periodic table? Yes, absolutely. We are not crazy. For sig figs, if we add and then divide, do we need to round and then divide? Good question. I'm going to say yes. Do we need to know the heat capacity of water? Nope, that'll be given. Can we go over collision theory? It's been covered. Wouldn't it be 21? I'm assuming that you're talking about this equation here. The reason why this equation is not... the reason why this answer is not 21 is because we've got to round to one significant digit, with 2 just being one sig fig. That's why it needs to be 20. So I'd look at this 0. Do I round this 2 up or down? For collision theory, we've talked about that up here, right? We need to look at how fast, like, how do reactions on the molecular level occur? These are your collision theory aspects. I also recommend reviewing the textbook sections for more information. Could you go over the specific, the sig fig log for sig fig rule for logs? Sure. We can also kind of just water this down for sig figs for acids plus bases, right? When you're doing these logs, or 10 raised to the negative pH slash POH, right? One of the two. You round. So your first step for these is to, 1, count the number of sig figs in your number. So however many sig figs there are, that's how many you count. The number of sig figs is the number of decimal places. You need. So let's do a example here really quickly. So let's do an example. Let's say I'm taking the negative log of, let's say, 2.3 times 10 to the negative third. All I do is I plug this into my calculator. I don't have a calculator next to me, so I'm just going to use my phone to calculate. So we have the negative log of 2.3 times 10 raised to the negative third. And we get 2.638 dot dot dot. But because we've got two sig figs, that means we need two decimal places, 2.6, and that would be 4 as our final answer. Do we use sig figs for temperature change and the specific heat equations? Yes. What are the sig fig rules for surrounding pH, and at what point in a long equation multi-step do you account for significant digits? Good question. Let's say for stoic, for instance, here. The real digit that you need to be concerned about for your stoic here is this guy. However many sig figs this has is how many sig figs your answer has. And that's the same thing for any of them. This one or this one. Now for this, let's say for this one, whenever you have different styles of sig fig stuff, for example, this one and this one both have different rules than your big multiplication, you need to round at your individual steps. You go over how to identify, yep, we've done that. If you've got Q water, need to solve for the delta T of the metal, what do you do with the final number? Do you add or subtract? If you're trying to find delta T of the metal, it would be division, because you need to isolate delta T at the end. Can you do an example with Q, negative Q metal is equal to positive Q water? Sure. A bang, bang. All right, let's party. Let's say we have the mass of our metal is equal to 100 grams. Let's say we've got the mass of the water is equal to, let's say, 42.0 grams. Let's say our delta T of the metal is equal to negative 72.3. And let's say our delta T of your water is equal to, let's say, I don't know, 6.2 degrees Celsius. And the specific heat of the water is 4.184 joules per gram degree Celsius. Now, with our equation, we can just, all we need to do is plug this in. So we have the negative 100 grams times, right, this side's all metal, times C times of the metal times the negative 72.3 degrees Celsius. And this is equal to, oh, no parentheses, 42.0 grams times 4.184 joules per gram degrees Celsius times delta T, which I believe was 6.2 degrees Celsius. Now, of course, these values will be given to you in the form of a word equation. They will not be presented in a nice fashion, just like how I've got here. But I'm doing it all right here, just so that way it's easy for all of us to see. So all we do now is we solve for C. So that means we've got the clear, we've got this way 100.0 times 72.3, which means we've got 7,230. C is equal to 42 times 4.184 times 6.2, which is equal to 1,080. 89.5136 divide 7230, and we get C of our metal is equal to 0.15 joules per gram degree Celsius. Don't forget to round to sig figs. That's what I've done there. And then you're done and dusted. Can we do that? Yep, done, done, done. I thought all acids are under 7. For pH, that is correct. All acids are under 7. What will be given on the test? What will not be given? We covered that. How many jumps is it from May to King? Is it in metric conversions? Oh, that's a good question. I was not expecting that question. I do still see we've got a lot of questions going down, even questions being submitted at around 5 minutes ago. So looks like we'll be going a little bit late. That's okay. For metric conversions, a lot of you use the mnemonic May King Henry die by drinking chocolate milk, Mike. So the specific question here is how many jumps is it from M to K? 1, 2, 3. So whenever there's a big gap like this, it is 2 jumps. Well, I guess technically 3 if you count it, right? You go 1 decimal, 2 decimal, 3 decimal places. That's it. Is Avogadro's number 6.022 or 6.02? Use 6.022 times 10 to the 23rd. Can we go over one practice of serial dilutions and specifically go over when you would use sig figs? Specifically, do you use sig figs in between each dilution or at the end? Good question. I can answer that sig fig question right now. That is for your, you only round at the end of those equations. You want to be as precise as possible until the end. For serial dilutions, I am going to say at since it is now 9:15, any questions submitted after 9:15 will not be answered. Just so that way we can finish on time and be ready to go. I want to make sure everybody who is taking the final tomorrow does get a nice rest and some sleep. We've covered mole ratio, covered the mole want, the coefficients, yes. Can you just teach the entire semester right now? I'm doing my best. But let's discuss serial dilutions. So serial dilutions, this uses this equation. M1V1 is equal to M2V2. So let's actually, I might go over to our other document here, the semester 2 study guide. Bear with me. Boom. Ah, perfect. So let's say this. Numbers, if you're following along, this is number 78 on the review guide. So this is saying a 15 molar potassium chloride solution is diluted. Solution A is diluted from is uses 40 milliliters, volume 1 of the stock solution M1 to 200 milliliters N2, or sorry, that's V2. Apologies. Now, me personally, I like to organize these first by doing. We've got solution A, then we have solution B, and then we have solution C. So let's talk about solution A. We need to find M2. And that's our whole goal. So this is saying we've got a 15 molar or M1, so 15.0 times 40 milliliters. Don't forget units in all of this. Is equal to, what was it, 200? 200.0 milliliters times M2. All you do for this is you just solve for M2. So divide both sides by 200.0 milliliters. And you get, pulling out the calculator, 15 times 40 divided by 200. And we get M2 is equal to 3.00. We need, generally, if it has a long running decimal place, we will keep the entire number throughout it, but this is nice because it just rounds to, it is actually 3 exactly. Here is the tricky part here. This 3.00 molar becomes M1 for solution B. So we've got M1, we've got the volume, V1 and V2. So we have 3.00 molar times 60 milliliters is equal to, sorry, 60.00 milliliters is equal to 300.0 milliliters times M2. Again, solve for M2. So we get 3.00 times 60 divided by 300. And this time we get 0.600 molar, which is equal to M2. And again, we follow the same trend using red. This becomes M1 for C. So we have 0.600 molar times whatever it is, 80 milliliters, 80.0, sorry, milliliters is equal to 120, or sorry, 1200 milliliters times M2. An important note here. This must be converted to milliliters because this one is in milliliters. They all need to be in the same kind of denotation. So either they all need to be in milliliters or they all need to be in liters. So we divide, again, I see hands being raised. I'm not answering any hand raised questions. We divide both sides by 1200. So we get times 80 divided by 1200, or not 2000, sorry, 1200. And we get M2 is equal to 0.0400 molar, which is our final answer. The reason that we have 3 sig figs here versus any other is because if we look at all of our values given, the least number of sig figs is 3. So that is what makes it useful for us. I'm going to go ahead and zoom out just that way. If anybody would like to take a screenshot, may. Again, this is how I set them up. This is how I make the key. So that way it makes it just easy for all of us to track. How do you find concentration? Good question. Now that everybody's had a chance to screenshot this section, we can calculate concentration using the molarity is equal to M over V. M, of course, stands for molarity. M, of course, stands for molarity. N stands for number of moles, and V is the volume. And that's all we have to do, right? So you just plug all these values in. M is molarity. N is moles. And V is volume in liters. So you just need to plug everything in and call it a day. Approximately how many topics of questions of each topic are there? Good question. It is pretty fairly balanced, but it is a heavier portion in the content that was recently covered. That is, of course, reaction rates and acids and bases, because you didn't have an exam on that one. Can you go over how to tell if something is a weak acid or strong base? We can, but it's not on the exam. I'm just going to skip it. Will you or MRS be in Corboy any days this week after school? I know I am not. I'm not sure about MRS's schedule, but I am available via email if you do have any extra questions. Can we go over naming acids? Can you also talk about how you name a base? For base naming, all it is ionic naming, but we can go over naming acids. And we are slowly getting to the end. We've got quite a few things here. Yes, you are given those formulas. A video will be posted after this meeting. You don't need to be talking about supersaturated, saturated, or unsaturated. Will reaction rate graphs or pH or pOH ever be negative? No. How lenient are we going to be for calculator errors with dimensional analysis? If you need to get the correct answer. Will we need to write word equations? Yes. Can you go over serial dilution? Just did that. Okay. Are MRS's or my test and MRS's test different? Nope. The only thing that's different is the extra credit. Sorry, we're answering a lot of these big, easy questions as we go. So that way we can kind of keep it going. Okay. For neutralization, why is it not H3O plus? That is only for your acids and bases and looking in your conjugate acids and conjugate bases. There's one question on thermochemistry. There's no questions on saturated, supersaturated, or unsaturated. Okay. I think we've hit a bunch of topics now. We've got like 5 questions left. So, apologies for the big thing right there. I just would like to end as close to 9:30 as we can. So, naming acids. There's 2 versions of acids that you need to be aware of for the exam. Binary and oxy. A binary acid. This is an acid with hydrogen and one other thing. So HCl, HF, H 2SO4, these sorts of deals. Or not H2SO4, H2S. That's what I meant to write. HCl. Whenever we're working with binary acids where it's hydrogen and one other thing, we always start with hydro. Always. Then we take the base of the word. So for chlorine, that'd be chlor. And then we always end in ic. So for binary, you start with hydro, then you do the base of the word, then you end with ic. So for HF, F is fluorine, so the base of it would be fluor, or in other words, hydrofluor. U comes first. Acid, and don't forget acid at the end. For HS, this one's a little bit more tricky because it is a one-time, it's one of the two big exceptions to our naming rules. The sulfur's base is just sulfur. So it'd be sulfuric acid. For oxyacids, these are your ones that contain oxygen as part of your kind of naming diagram. A good hint is anything that contains a polyatomic is a oxyacid. So good examples of this would be HNO3, HNO2, H2CO3, and H3PO3. So this one does not use hydro. So for oxyacids, you don't need hydro. So we've got HNO3. So we look at the base of the word, base of anion, and then we add one or two things. If the anion ends with 8, you change the ending to ick. A good way to remember it is I ate something icky. So for HNO3, this would become this is a nitrate, so it become nitric acid. But if it ends in, we'll change this color to beige. If the anion ends in ite, you change it to OUS. So for NO2, this is, of course, nitrite. So it would become pink, OUS, acid. HCO3, even though there is a 2 here, it doesn't matter. We don't care about it. All this would become is carbon because it's carbonate. So it'd become carbonic acid. H3O, H3PO3. Phosphorus is one of the other exceptions to our big rules. So this is phosphite. So it'd become, technically, if you were doing these rules by looking at it directly, it'd become phosphoric acid or phosphoric acid. But it is special. Phosphor, and this would become OUS acid. Zooming out for people to take a screenshot. We talked about that one. We talked about that one. We talked about this one. Can't cover this one because it was just delivered after 9:30 or after 9:15. Can you go over activation energy with exothermic graphs? We can. It's going to be a very short and sweet one. So let's say you want exothermic. I know this is such a great graph. We okay, so activation energy. If you recall, activation energy is how long or how much energy does it take to get to that pump right there. So we would do final minus initial. So activation energy is equal to final minus initial. So, or in other words, in this case, it'd be 75 minus 50. So EA is equal to 25 kilojoules. Will H plus or OH minus concentrations ever not need to be in scientific notation? It is standard practice for any H plus or OH concentrations to use scientific notation. Last question. What about once you isolate delta T? If that is the change in temperature, what do you do with that to add to the final temperature? So that is relating to, I believe, this question here. If we were to isolate delta T, the question would ask, like, what is the change in temperature for either the water or the metal? It would not ask for the final temperature or the initial temperature. If it did, you would just need to subtract. And that is it. That is all of our questions we've gone through. I'm going to go ahead slowly. We're going to start up at the top. For anybody who would like to take a screenshot of this, if you are in a different class than mine, I will still send this over to MRS and our folks down at the Learning Center, just so that way they can distribute this should they choose. I will also be uploading this recording up to Schoology to YouTube, so that way, and I will also be sending out those links to all teachers. If you have any further questions that were not covered in this, shoot me an email. And I am happy to answer them for you. I will not answer them probably tonight. I'm going to go to bed, but I will answer them tomorrow morning prior to any exams. So, first page, we're going to scroll down. Second page, third page, and the bottom of the fourth. Again, I hope you thought this was helpful. The recording will now end. Thank you so much for stopping in, and I'll see you all in passing.